All right. Hi there to everybody watching the recording. I did want to mention a couple things, questions that we addressed in the first minute here. WebWork problems 10.1.4 and 10.1.9 appear to be broken. If I'm able to fix them in the next day or two, I'll let you know so that you can still do them for your homework. If not, I just won't count them toward your grade. So no need to email me about it. I know there's a problem. And I'll let you guys know if I fix them, but you can, it's not going well. So you can probably assume that you don't have to do them, and I'll let you know if that changes. The other question was regarding Euler trails and Euler circuits, which is, which WebWork question was that, Amber? Was that 10.2.3 or something? Remember which one that was?
It was a couple. I think it was like 1, 2, 3, and maybe
Okay,
5.
10.2 numbers 1, 2, and 3. Okay, so the definition of trail and circuit, Euler trail and Euler circuit in your book says that the two things are mutually exclusive. It says that an Euler trail has to start and stop at different points, whereas an Euler circuit has to start and stop at the same point. And that's not the interpretation that WebWork is using. WebWork is using the interpretation that an Euler trail may or may not start at the same point, whereas an Euler circuit is the same. It does have to start and stop at the same point. So to summarize, in the WebWork questions, anytime that you have an Euler circuit, you also have an Euler trail, right? And that's a little bit different from the terminology that the book uses. So I wanted to alert you to that. Okay, so those are the questions here. And let's jump back into 10.2. So maybe what we should do is do a little bit of practice here. Remember, we were talking about Euler circuits last time. And so we can do some practice here. Pop this over. And let's do these ones actually. There we go. Okay. So I like to see if you can tell me whether each of these graphs has an Euler circuit, and if so, what's the order that you go through the vertices in order to find it, right? So does the graph in number 23, do you think that one has an Euler circuit? Oh, and I'm sorry, David, you had a question. Is there one way to interpret a trail that's more common? Yeah, your book is doing it wrong. WebWork is doing it right. In general, in graph theory, an Euler trail means you may or may not start at the same point. It could go either way. And so that's why the WebWork is one way and your book is the other. Your book is doing it kind of a weird way. Yeah, it's a great question. Okay, so in 23, do you think we have an Euler circuit in there? No. Okay, why not, Amber? Good. There's a vertex with odd degree, V0, right? So remember last time we were saying that an Euler circuit requires that every vertex in the graph has even degree, right? Okay, how about number 24? Is there an Euler circuit in here? No. Okay, why not? G has odd degree, right? This G in here has degree 3, right? So that excludes that one. Okay, what about 25? Does this one have an Euler circuit? No. Okay, and why is that? C has degree 5. Good. How about an Euler trail? Does 25 have an Euler trail? Yes, from A to C, right? So remember, an Euler trail is a trail that touches every edge, okay? So what we want to do is we want to go through, and actually let me redraw this so I can highlight it here. So we have two diamonds. Oops, sorry. There we go. So we have two diamonds, one with a line through the middle. There's our graph, right? And an Euler trail touches every edge, but it can start and stop at different points. So David, it seems like you're saying we want to start at A and then stop at C. Is that right? Start at C. Okay. So if we want to start at C, so now let's put in the Euler trail. Now we want to touch every edge exactly once. You can't miss any edges. You can't go over any edge twice. So I'm going to highlight them as we go through, right? So we're going to start at C. Where would you like to go next? Okay, D. Okay, then there's only one choice, E, and then only one choice, G, and then only one choice back to C. Okay, so now what do we do? Around the perimeter. Okay, so then we can go up to B, A, F, back to C, and then there's only one choice left, over to A, right? So you can see that every vertex in this graph has even degree except for A and C, which is why A and C are the starting and stopping points, the ones with odd degree, right? What do you guys think? Does that look good? Questions? Okay, so then let's try another one. Number 26 here. Does number 26 have an Euler circuit? No, because D has odd degree. Okay, so this one has odd degree, right? Are there any other vertices with odd degree? So it does not have an Euler circuit, right? But if it has two vertices with odd degree, then we could do at least an Euler trail. F, E, and J. Okay, so let me just, so there's J, F, E, and D. So those are the ones with odd degree, right? So let's say that I wanted to keep this graph as intact as possible, but modify it. But so I want to remove the minimum number of edges so that I can have an Euler trail. Which edge would I want to remove in that case? E to D. Yep, that's one that I could do. What's another one that I could do? So ED is one edge I could remove. The other one? Not IJ, because if I do IJ, it'll fix J, but then I will become odd, right? Which would, yeah, right? So EF is the other one that I could remove, right? So I could either remove ED or EF, and either of those, if I remove it, then I could at least get an Euler trail out of the thing, right? So let's try that. Let me see if I can recopy here. Oh boy. You know what would be better? Here, I'm going to do this. This is dumb. I'm going to pull up a digital copy of the book and use Paint to draw on top of it, and that will be way easier. Just give me one moment here. One second. Let me download my copy of the book here. I think that'll be useful today. Oh, the snip tool. Oh yeah, I should do that. That's actually it. Well, too late now, but maybe I'll do that in the future. That's a good idea. Thanks, Amber. Yeah, that's a good one. Okay, so let me share screen. Okay, great. Let's bring up this guy. And I'll bring up my chat window here. Okay, let's press this one. Yeah, I think this will be useful later too, to look at some stuff in the book here. Great. Okay, so there's number 26 that we were looking at. Zoom a little bit. Oops, oh boy, oh, I screwed up. I got it right on the page before. There we go. Okay, great. Cool. Okay, so let me get my other window up here. Wonderful. Okay, cool. So grab this. Open it in Paint. And now if I get rid of, or actually let me zoom a little bit. Okay, now if I get rid of ED, for example, I should be able to find an Euler trail in here, right? So let me grab red and pencil. Okay, great. So where's my Euler trail gonna go? Like, where should I start? So one more Euler trail here. Where should I begin? F or J. Okay, so let's start at J. And so I'll start here. Okay, great. And so where should I go next? Let's put the trail in. Okay, H and then G, sure. Okay, well then I only have sort of one choice here. We go up to D, then to C, then to B, and then I have another choice. So what should my next choice be after B? A, J, I, okay. And up to A, then to J, then to I. Great. And then? B, E, F, B, E, F, H. Almost. And then I and F. Perfect. Now, what I wanted to show you in this one is that you can't screw it up. It's actually impossible to screw up this drawing this trail. There's no wrong way to go. Let me show you what I mean. Back here, I had a choice at B. What if I make another choice? What if instead I go to E, right? So I go E, then F, I have another choice. Again, it doesn't matter which one I pick, as long as I don't go back to F on accident. That's the only thing I can't do, right? So I could go to I or H, either one of those is fine, right? So if I go to H and then to I, that's cool. I can then go around this trapezoid and back to F, right? Or I could go to I, right? And then I would go around the trapezoid the other way, like this, and then back to F. As long as I don't go back to F early, right? As long as I don't do this, right? And go to the stopping point before I'm done. As long as I don't go there, then any other path that I pick is going to be totally fine. Now that's for an Euler trail. What about an Euler circuit, right? So with an Euler circuit, let me give you another example. With an Euler circuit, there's no way of breaking it at all, it turns out. So I think those are up here. Yep. Okay, perfect. So number 12, for example, does this one have an Euler circuit? Yes, right? Every vertex has even degree. 2, 4, 4, 4, 2, right? And in this example, I can literally start at any point. I can literally make any choice. And no matter what happens, I'm going to be forced to draw an Euler circuit. Okay, so let me give you you tell me, where should I start and where should I go? And you can pick totally randomly, and it's going to turn out to give us an Euler circuit. So what do you guys think? Where should I start? V5. Okay, so I'll start in the middle. And which way do you want to go? Maybe give me an edge number, because there are different options here. So from now on, why don't you give me edge numbers, and I'll go down those edges. So what do you think we should do next? E3. Okay. Let me do it in red, actually. Easier to see. Okay, E3. Okay, and then? E2, okay. So we'll head back to V5. Okay, so from here, we're forced to take 6 or 7. And again, it doesn't matter which, right? So I'm forced to take 6 or 7. I'll just choose 6. Now I could go either way. Why don't I go over this way? Okay. We'll do 8 and then 1. And then again, I'm forced to take 4, which is fine. And then 5, and then back up the other side of the loop, back up to V5. And you can see that I do have to take a certain path at some points, and at some points I have choices, right? Sometimes I'm forced, and sometimes I have a choice. If I'm forced, well, then I'm forced. Then I go the way I'm forced to go. But if I have a choice, I can literally make any choice I want, and the Euler circuit will still pop out. Can someone explain to me why that is? Besides going back early. Oh, that's only for the trail. So on a trail, I can screw it up if I go back, if I go to the ending point early, or if I go back to the starting point. Well, no, I can't go back to the starting point. No, if I go to the ending point early, I can screw up the trail. But my claim is that it's impossible to screw up the circuit, right? Even if I try to go back early, I still won't be able to screw it up. And my question is why? The number of edges available to leave or arrive at. So you're on the right track there, Amber. Can you say more about that?
Yeah, I'm just thinking you need to be able to do it in pairs. And so if we have even degree, then we'll always have a way to do that pair of arriving and leaving.
Yeah, so let me rephrase a little bit. I think there's always going to be a way out, right? I think that's what you're getting at, right, Amber?
Yep.
Yeah. So no matter which way you go, because every vertex has even degree, there's always a way out. There's always an escape route, right? And David, you had a question. Okay, what if we start at V3? So you want to do a particular example. Okay, so V3, okay, and then go V2. Oh, you proved me wrong, dang it. Oh, you're totally right. V4 and then back to V3. Nope, okay, I lied. Very nice, right? So there, you just missed the entire intersection. Inner, not intersection, but inner section, right? The section inside. Yeah. Okay, so what went wrong there? Is there a way that we could sort of modify our algorithm for finding an Euler circuit so that it's unbreakable? It looks like David broke it there. That was great. Nice work. So can we fix it? Has anyone ever heard of a greedy algorithm before? Does anyone know what that is? You have to choose the edge to a vertex that has more connections. I would say greater degree, right? When possible. Yeah. So what if at every choice, we can still start anywhere we want, but what about now if at every choice we always go toward the vertex with the highest degree of edges that we've not touched yet, right? So if I start at V3 and go to V2, right? Well, V1 has degree 2 of edges we haven't touched, but V5 has degree 4 of edges we haven't touched. So in that case, we would be greedy to go to the biggest number of degrees, right? Here, we would be greedy and go to the biggest number of degrees, which would be 4. Let's go this way. And now what have we got? Now we've got degree 1 left, 1 remaining on V3. We've got 2 remaining on V5 and 2 remaining on V1. So it appears that if we use this greedy algorithm, I can do either 5 or 1, which I think is true in terms of completing our picture and actually making it to the end. I think that's the right sort of setup. I could go either way and complete my circuit with either choice. So let me go back to V5, I guess. I'll just choose this one. So there, now I only have one choice. Let's go here to V2. Now I only have one choice to V1, and then V4, and then V3. So what do you think? Do you think if I use the greedy algorithm that resolves our problem and that's going to work? Or do you think it's still broken? Yes, you think it works now? Anyone disagree? Anyone have another counter example? I'll let you guys think about it. That's a fun one, right? So David, that was a great catch with the counter example there. Okay, let's try just one more. Well, let's not. I'm good on that. Let's move on. So besides an Euler circuit, you could also have a Hamiltonian circuit, right? So can someone explain to me what a Hamiltonian circuit is while I set this up? It's a simple circuit, okay. So that means that you start and stop at the same place, and you're not allowed to repeat any edges, right? Are there more restrictions here on simple circuit? Let me go back to the definition. So it doesn't have, a simple circuit has no repeated edges and no repeated vertices, right? And a Hamiltonian circuit is a simple circuit where every vertex appears once. So Nathan and Amber, together you got the definition. Let me summarize. A Hamiltonian circuit touches every vertex exactly once and every edge at most once. You don't have to touch every edge, or you could leave some out, okay? But you do have to touch every vertex exactly one time. Yeah? And you have to, of course, start and stop at the same place for it to be a circuit. That's why it's a Hamiltonian circuit, not a Hamiltonian trail or something, right? Okay, so here's the game. We've got these two graphs. I want to find a circuit, so start and stop at the same point, where I touch every vertex exactly one time. Now, if it's a circuit, it doesn't matter where I start, right? So let's say I start, up here at V0. Let me make that red, okay? So I start at V0. It doesn't matter at the very first step which way I go. So I'll just go down, make that big again. There we go. Let me just go down to V6. Okay, so what should I do next? Go to V1. Okay, so I want to go across to V7 to V1. Okay. Where should I go after that? V2 and V5. Okay. And then? V3, V4. Ooh, I don't want to go 3 and then 4. That's going to trap me. So if I go 3 and then 4, now there's no way out except to hit either 5 or 3, which I'm not allowed to touch those vertices twice. So what do I have to do instead? Instead of 6 to 7, go V2. Well, I don't have to backtrack. I can keep the path I have already, and I can still make a Hamiltonian circuit, actually. So I could backtrack, and that's fine, but I don't have to. Can you see how to get the rest of the Hamiltonian circuit from where I'm at now? Oh, I can't. No, I'm sorry, you're right, because of V1, right? I was going to go around this way and back up, right? But I can't do that because I already touched V1. Okay, so let's get rid of some stuff. Okay, so you want to go, instead of V6, we go to V7. Go to V2 instead. Okay, so I'm going to V2. Okay, great. So now what do I do? And V5, okay. And then I guess I only have one choice now, right? Because I can't go to V6, I already touched it. So I got to go to 4. And then again, I'm forced to go to 3. And then again, I'm forced to go to 1. And now what do I do? Then 7, then 0. Very nice. There we go. So there's a Hamiltonian circuit, right? It's sort of the idea is, without taking your pencil up off the page, touch every vertex, but not necessarily every edge, right? So without lifting my pencil, I go around and I touch every, oops, I'm sorry, getting a little messy there. It's hard to do this on a trackpad, right? Okay, so let's do the same thing for 24, right? Again, I can start at any point, so let's start at A. So what should I do next? LKI. Okay, sure. So we got LKI. Okay, and then? HBG. AB, I'm trapped now. Yeah, we missed J, right? So, okay, so you want to go to J instead. Okay, which I guess then takes me to E, and now I'll let you guys take over. Okay, so where would I want to go from here? To D, okay. And then I have to go to C. Now I have some choices. You said F and then I, okay. And then HGBA, very nice. And here's what I want you to notice about these guys, right? What they're sort of doing is they're making a shape that's in some sense, like you're trying to make like the exterior of a shape in some sense, right? There's this sort of inner region. Let's see if I can do this. There's this sort of inner region. Oh, that's not going to let me do it because it's a JPEG. Well, there's, here, let me do it this way. Where's a big brush? Right? There's sort of this inner region, right, inside of here. And we just sort of go around it, right? This is like the outside of it. And I have a similar region right through here, right? And I just sort of draw around the exterior of that region. Really what a Hamiltonian circuit is, whether or not a graph has a Hamiltonian circuit, what that's asking is, can we sort of split this thing up, or not split it up, can we trace out a shape around the exterior of the graph, leaving an interior section is sort of, I think, a nice heuristic, a nice guessing, a way to guess of where to go, right? You don't ever want to go sort of you don't want to create regions where there's multiple inner regions is sort of a way to think about it. I'm saying this badly. Does that make sense? Where you're making an exterior around the graph. I mean, you can see that BC, of course, is more exterior than HI, right? But that's not quite what I'm getting at. What I'm trying to say is you're able to trace around a single uniform region, right? And make a circuit, right? That's why it's called a circuit. It's because you have a circle. So maybe it'll help if we do some non-examples, right? And of course, I'm happy to take questions. So please holler out if you got questions. Let's try some of these guys, right? So I'm supposed to show that these don't have a Hamiltonian circuit. So let's try that. Okay. Something regarding area. No, Amber, I'm not quite sure what you mean. Yeah, if you can think of any other vocab terms or hints, happy to think about it, but I'm not sure what you mean there. Maybe not. I guess we'll see, right? So why does 25 not have a Hamiltonian circuit? Can someone explain sort of what's wrong with number 25, or even tell me which vertex is problematic? C is problematic. Very nice. Why is C problematic? Yeah, it's a choke point, right? So what I was talking about before with that exterior, if I try to go around the exterior of the shape here, right? well, then what I'm doing, what the graph forces me to do is come back to touch a point that I've already touched. There's you can think of this as being, you know, kind of like a blob, but a blob that was pinched in the middle, right? So this could have been, you know, it could have been a hexagon or something like that, but instead we sort of pinched the center, right, from top and bottom down into the single point C, which means there's no way to continue my journey along the exterior of the graph without retouching that point C that's problematic, right? Does that argument make sense to people? Are people happy with that? Yep, okay, cool. So what about this guy, 26? Does anyone see where the choke point is? That's not a technical term, choke point. Amber just made that up, but I think it's a great description. Does anyone see where? Yeah, B or C? Yeah, I think B is our problematic node here, right? And why is that? Well, if I try to trace the exterior, let me start at A. I'll go around here, tracing the exterior. Oh, well, I can't really do that, huh? Okay, so I can't go that way. So maybe I'll do, you know, I'll try to go around here and then back through. But now, you know, I have sort of two options. I can go the C way or the E way, right? And either way, if I take C down to B, I'll get trapped in the middle, right? So I don't want to do that. But if I go to E and then around the middle, well, then I've skipped C, right? And the reason why is because there's two shapes that share a point. There's this square in the middle, and then there's this big one on the outside, right? And there's this choke point at B, right? Because the square in the center is sharing this point with the outer square rather than having A and C being connected, right? So in some sense, it's a little bit like the Euler circuit because, you know, as you're tracing around a shape, you need to be able to enter and exit that shape, right? And B is not allowing that to happen in this case, right? What do you guys think? Does that make you happy? Questions? Makes sense. Okay, cool. Let's try one more. Oops. Ah, dang it, I did it again. Can I undo that? Oh, shoot. Okay. Sorry, screwed it up. That's 10-4. Okay, almost back. There we are. Cool. Okay. So here's 27. Where's the choke point? Yeah, B again, right? Because we have this outer shape, the sort of house shape, then we have this inner shape of the triangle, and B, there's only one point connecting them, right? Cool. Okay. Oh, darn it. Keep doing that. Just the worst. Sorry. I'm gonna stop being dumb. Okay. Just do it all the time. It's so annoying. Yeah, exactly. Yeah, no, common problem, I'm sure. Okay. So which of these have Hamiltonians and which ones do not, right? So let's start with 28. Do you think this one has a Hamiltonian? No. Okay, good. Why not? Yeah, so here they share 2 points, right? The diamond, I would say the diamond and the, or even the diamond and the hexagon, but it's not really a hexagon. It's more like a diamond and the, this would be a chevron, actually. A chevron is like something that looks like this, like a greater than or less than. This is kind of like a, a 2D less than sign, right? So when I'm going around, I do have 2 shared points between them, but that doesn't seem to be enough, right? If I try to go around the outside of the hexagon, of course I'll miss D, right? And if I make sure to account for D, let's say I start at it, right, to make sure that I get it. Well, if I start at D, then B or G, it doesn't matter which way I go, the thing's symmetric, right? So if I go to B, then I can either go back around, and if I go to C, I won't have any way out. And if I go to D, I'll skip C, right? So there's no way to get them all. What about 29? Yes. Okay. So what's the order of your path there? Actually, while you do it, let me make a picture. Okay, so you want to go B, C, D, E. Okay, sorry, let me get set up here. Okay, B, C, D, E, F, G, A, B. Very nice. Makes a little Pac-Man. Great, great work. Okay, what about 30? Got to use arrow keys instead of the mouse. That'll save me from making that mistake. "30, you say no. I think I see one, actually. You think yes. Nathan, do you see it? Oh, you were looking at 31. Okay, yeah, let's do 30. Okay, so you think 30 does have one. Okay, so where's the one for 30? Okay, 1, 5, 4, 7, 6, 2, 3, 0, 1. Very nice. Okay. And then, so then you were saying for 31, it does not have one. Is that right? Does not have one. Okay, why is that, Kobe? Okay, if I do B, C, F, G, H, E, A, it misses D, right? So D is going to be skipped if we hit the middle, right? Cool. Okay, yeah, that's a good one. So a good practice for you guys that I would recommend is these questions. Give examples of graphs that have Euler circuits but not Hamiltonian, or Hamiltonian but not Euler. Then examples that have both, and examples that have neither. Oh, no, I'm sorry, this one doesn't say neither. It has an Euler circuit and a Hamiltonian circuit, but they're not the same circuit, right? So I think drawing some sample graphs that satisfy these guys is really nice practice here. I think that'll really get your brain sort of in the right gear to be solving these problems. Any questions there? Does that all look good? Looks good. Okay. So let's see what else we've got here. Oh, and then there's all the proofs. Okay, so I think we're good on that. Okay, blah, blah, blah. Cool. Okay, so let me stop sharing. Go back to video here. And from there, I think we should get into the next section. So that was all about walks, trails, paths, and circuits, Euler circuits and Hamiltonian circuits. Those are all the different kinds. And now I'd like to get into some linear algebra, which I bet you didn't think we'd be doing that, did you? Right? So it turns out that, there's a question here. Are there any algebraic tricks? There's a whole study of Hamiltonian circuits and whether or not a graph has one, and it's actually a really complicated set of issues. So I definitely would recommend doing a little bit of reading. So if I was to, here, let's go. Let's do this. So if you just go to Wikipedia, and want to check out a ham path or ham circuit, right? There's all kinds of properties, right? And you can, and it talks about Eulerian circuits, right? Which is an Eulerian tour passing through each edge exactly once. That will give you a Hamiltonian circuit, right? So every Eulerian graph is also Hamiltonian, but you could have a Hamiltonian circuit without it being Eulerian, right? So it's like a square is a rectangle, but a rectangle is not necessarily a square. Right? The reason for that is because anytime you have an Euler circuit, right, that means that you're touching every edge, which means that, of course, you must be touching every vertex if you're touching every edge, right? And again, you're not repeating edges. So, so you can get one that way, but there are other ways that you can get it as well. So that's just one sort of little example of the complexity of the relationship between Hamiltonian and Eulerian circuits. Right? And you can read all about these different theorems. There's, you can connect Hamiltonian circuits to vertex degree. Hamiltonicity has been studied in relation to density, toughness, forbidden subgraphs, and distance, among other parameters, right? So, the density of a graph or the toughness of a graph is a whole thing, right? Yeah, fun reading. It's pretty interesting stuff, right? Forbidden subgraphs, yeah, that's great, right? Which really, Amber, I'm glad you mentioned that, because really what that's talking about is choke points, right? Because what we were saying with those choke points is, hey, there's this one shape and this other shape, and they're connected at this single point, and you can't do that point twice, right? And so each of those two shapes that are connected, one shape is one subgraph, the other shape is the other subgraph, right? And they're connected up in this certain way, which is forbidden, right? So that's a really, yeah, I'm glad you mentioned that, right? So, obviously that's a pretty, not to be disparaging, but that's a pretty obvious thought, right? Is that, okay, well, if you have this sort of choke point situation, you can't have a Hamiltonian. And so people have been thinking about that for, whatever, almost 200 years now. And so obviously people, thought of that and have done this whole investigation as to like the particular rules that govern choke points and how they work. And people have written all about that, right? So yeah, so that's great. It's a whole thing, right? Cool. Okay. Yeah, absolutely. So let's talk about matrices for a minute. Now, but before I get into the whole matrix shtick, let me tell you why we're doing this, okay? This is kind of a complicated one to start with. Let me start with this guy. Let's start with this graph, and I'm going to number the vertices here, 1, 2, 3, and 4, right? Just for some context here for me and how gauging how fast I should go, how many people in here have taken linear algebra already? Maybe say yes in the chat, or you could click the little yes button if you want. Okay, 3 yeses, 5 yeses. Okay, no one did that. Okay, so it looks like most of you have, of the ones that said something. Okay, so I'll go, I won't go too fast, but I'll just go a little bit fast. You remember nothing. Okay, all right, fair enough. So that's kind of a half, a 0.5 response from David. Okay, and you haven't. Okay, so what we're gonna do is we're gonna talk about matrices. Okay, now a matrix, and just to be clear about the terminology, a matrix, like a vertex, has a plural that's weird, okay? So you don't say vertexes, you say vertices. You don't say matrices, you say matrices, right? There's another one now that I'm forgetting. Oh, indexes. You don't say indexes, you say indices, right? It's all Greek words, right? So here we're gonna be talking about matrices. And all that a matrix is a table of numbers. That's it, right? So if I have, and the syntax is that you enclose it in square brackets. So if I have, 2, 1, 3, 6, 8, 9, right? So that's a 2-row, 3-column matrix, right? So you could have a square matrix. Here's a square matrix, right? Because it's 2 by 2, right? And all it is just a table of numbers, right? Now, what we're going to talk about is called an adjacency matrix. Adjacency matrix. And what that's going to do is it's going to provide an encoding for our graph in a matrix. Now, here's how it's going to work. The size of the matrix, or I should say the shape of the matrix, is always going to be square for our encoding. And the size of it is always going to be equal to the number of vertices. So in order to encode this matrix, encode this graph, I'm going to need a 4 by 4 matrix. Okay. Now in this matrix, there's going to be, there's going to be rows and columns, 4 of each. And what I'm going to put in this matrix, usually you don't put these numbers on the side. I'll just do it for this first example, right? These numbers indicate whether or not there's an edge between these two, the two vertices that correspond to the row and column of the entry. So for example, there is no edge from 1 to 1. I'm going to actually modify this a little bit. Okay, cool. There's no edge from 1 to 1, right? So I put a 0 there. From 1 to 2, there's 1 edge. From 1 to 3, there's 1 edge. And from 1 to 4, there's no edges. Okay. Why don't you guys do the next row? How many edges are there from 2 to 1? 1, good. From 2 to 2? 0. 2 to 3? 2. 2 to 4? 1. Okay. How about 3 to 1? 1. 3 to 2? 2. 3 to 3? 0. And 3 to 4? 1. Okay. 4 to 1? 4 to 2? 1. Oh, you said 1. Okay, sorry. 4 to 2 is 1. 4 to 3? 1, and 4 to 4, 1. Very nice. So this graph can be expressed by this matrix. Okay. Now there are some properties of the graph and properties of the matrix that cross over, and you can sort of interpret the graph in terms of the matrix in a variety of different ways. And there's a name for this. It's called spectral graph theory. Okay. And what spectral graph theory is, it's the study of graphs using matrices to represent them. Okay. So let's go through some properties here, right? For example, if I had a simple graph, okay, no loops, no parallel edges, right? That's going to mean something about my matrix. So first, let's talk about loops, right? If my graph doesn't have any loops, what does that mean about the corresponding matrix over here? They're all zeros on the diagonal, right? So here's the diagonal of the matrix. And by the way, for those of you that have not had linear algebra, the diagonal is the top left to bottom right. This is what's meant by the diagonal, not the other diagonal. We never mean that one. We always just mean this one, right? And if the diagonal here is all zeros, that means that there wouldn't be any loops, right? Because there's no edge from 2 to 2 or 3 to 3. And if we didn't have that loop here, there would be no edge from 4 to 4, right? How about parallel edges? How do those get represented over here? Or let me phrase it differently. If I wanted to say that there's no parallel edges in the graph, what would that mean about the corresponding matrix? Yep, every entry is either 0 or 1. And of course, I can't have negative ones in here, right? Because you can't have like a negative number of edges, right? So David, I take your point. If all the entries are less than or equal to 1, then we wouldn't have any parallel edges. So if every entry is less than or equal to 1, and on the diagonal it's all zeros, that would be a simple graph, right? Or a matrix that corresponds to a simple graph, right? Okay, but the sort of connections go much deeper than that, okay? So there's another example of a connection here, which is that there's a certain kind of symmetry that every adjacency matrix is going to have. Someone tell me what that is or how that works? So does anyone see any symmetry in this matrix here? Yeah, over the diagonal, good. If I take this guy, right, and flip it like that, right, you can see here that these ones are the same, the twos are the same, the zeros and the corners are the same. These ones correspond to these ones, and these ones correspond to these ones. Does anyone know the definition of a symmetric matrix? Does anyone know how it's defined? How about this? Has anyone ever heard of the transpose of a matrix? You know what that means? We switch the rows and columns. Good. So for example, if I was to take the transpose of this matrix here, transpose, right? Then I would have this situation where the first row becomes the first column and the second row becomes the second column. So this matrix transposed turns into this one, right? So how could we define a diagonally symmetric matrix in terms of the transpose? Good, they're equal, right? If a matrix equals the transpose of that matrix, that's true if and only if M is what's called symmetric. Cool. Okay. And every adjacency matrix must, adjacency matrix from a graph, right, must be symmetric. Why is that? Yeah, if x is connected to y is connected to x, right? So in a graph here, if 1 connects to 3 with one edge, right? Well, then of course 3 connects to 1 with one edge. Well, what kind of a graph would not have a symmetric matrix? Yeah, directed graph, exactly. So an undirected graph has a symmetric matrix, but an undirected graph has a symmetric matrix, but a directed graph, let's say I did it this way. Well, this one's going to be a bit different, right? So let's do the matrix here. 1, 2, 3, and 4. 1, 2, 3, and 4. Okay. 1 goes to 2. Let's put some loops on there as well. Why not? And let's put let's make some of these bidirectional, and let's do a parallel edge as well. Okay. So 1 goes to 2, 2 goes to 1, 1 goes to 4, and 1 goes to 3, but not to 4. Okay. 2 goes to 1, 2 goes to itself, and 2 goes to 4, but not to 3. 3 goes only to 4 and nowhere else. And then 4 goes to 1 and nowhere else. And you can see that's not symmetric anymore, right? What do you guys think? Does that make sense? Questions? Okay, cool. So obviously there's some really interesting relationships here between graphs and matrices. And now at this point, let me take a little diversion and just talk about matrices just by themselves. And then we'll circle back and talk about graphs again toward the end, right? So go like this. Okay, so let's talk matrices for a minute. You can treat matrices in the same way that you do for numbers. To wit, you can do arithmetic on matrices, okay? So let's say I want to add 2 matrices. So I have this one, 1, 2, 3, 4, and this matrix, 4, 5, 6, 7. And I want to add them. How does that work? Does anyone know? Add the matching components. Good. So in the top left answer, I'm going to add the top left numbers. So 4 plus 1 is 5. Okay, so what goes here on the top right? 7, good. Down here, 9, great. And then in the bottom corner, 4 plus 7 is 11. Beautiful. Okay, subtraction works the same way, right? If I had, 2, 9, 1, 6 minus 4, 8, 7, 5, what am I going to get? And in general, as you write a matrix, you do it the way that you would read English. So left to right, and then top to bottom. So I would go top left, top right, bottom left, bottom right. So I always go, I write out the numbers in a matrix the same way that I would, just in reading a page of English. Okay, so what have I got in the top left? Okay, -2, 9 minus 8 is 1, 1 minus 7 is -6, and 6 minus 5 is 1. Very nice. Cool. Okay, so that's addition and subtraction. How about multiplication, right? Well, that's where it starts to get horrifying. And if y'all have done linear algebra, you remember this. Let's do an example of matrix multiplication. Let's do this. But yeah, I'll just do the full square. That's fine. Let's do the same example. 1, 2, 3, 4, 4, 5, 6, 7. Okay. And just talking about the top left entry, okay, what's going to happen there? Anyone remember how it works? Anyone have a numeric answer for me? You don't. Okay. Let me start with a simpler one. Okay. What if I just have a row vector like 1, 2, 3 times a column vector like 4, 5, 6? Does anyone remember how to do that? Anyone remember the dot product? You know what that is? Yeah, that you just Googled dot product. Okay, nice, good timing. Okay, so what we're going to do is we're going to take the sum of the products of all of the entries. Okay, so what you want to do is you want to multiply these guys, right? Just like you were adding the ones before, we want to multiply them, but we want to take a sum of the products from I equals, let's say this is, 0, 1, 2, this is 0, 1, 2. Those are the index numbers, the position numbers, right? From 0 up to whatever the size is, 2 of m I times m n I. Call these matrices m and n, right? So what I'm going to do is I'm going to say, okay, I go to the 0th entry in m, the 0th entry in n, and I multiply them. 1 times 4 plus 2 times 5 plus 3 times 6, which in this case is going to be 4, 14, and 18 makes 32, which would be its own number. This would be a 1 by 1 matrix, right? So if I say 1, 2, 3 times 4, 5, 6, a row times a column, that's just going to be a single number inside the matrix, okay? Now what I'm going to do here with the 2 by 2 matrices is each entry in here is going to be its own separate dot product. This is just one. This is a single dot product. And every one of these 4 entries is going to be its own separate dot product. Okay, here's what I'm going to do. The row number of this determines the row that I use on the right. And the column number here, I'm sorry, the row number of my answer gives me the row that I use on the left. The column of my answer gives me the column that I use on the right. So what I'm going to do is the dot product of 1, 2, and 4, 6. So I have 1 times 4 plus 2 times 6. And that gives me 16. 4 plus 12, just like you said, Tamara, that's exactly right. Okay, so for this one, I'm still in the first row, but now I'm in the second column, right? So you said 5 plus 14, you're exactly right. So that's going to be 19. Okay, next, we're on the second row now. So we'll do the second row, first column. So 3 times 4 is 12. 4 times 6 is 24, so that makes 36. And finally, second row, second column, I have 15 plus 28, which is exactly what you said, Tamara. That's perfect, which is going to give me, 43. And that is how you multiply matrices. Gross, right? What do you guys think? Questions so far? You're starting to remember now. Excellent. Yeah, very nice. Okay. So what if instead of a matrix times a matrix, I just do a single number? You can even think of it as a single matrix, right? So if I do, I won't think of this. Well, there's another thing I can do, which is called scalar multiplication. So for example, if I said 10 times, 1, 2, 3, 4, I'm just multiplying by a single number, right? Then what I'm going to do is just multiply each of these entries by that number. So this is a little bit more like the addition or subtraction. This one's easy. It'd just be 10, 20, 30, 40. This one is called matrix multiplication. This one here. This one is called scalar multiplication. So there's two kinds of multiplication when you're talking about matrices: matrix multiply and scalar multiply. And they work differently, right? Now, when you're multiplying matrices, you have to be careful, okay? Because you'll notice when I multiplied the square matrices, that worked. When I multiplied the row times the column, that worked. But what if I did something like this? If I said 1, 2, 3 times the column 4, 5, 6, 7. What's going to happen there? Ideas? Does not exist. Good, right? In order to multiply matrices, you have to have the same number of entries because this 7 doesn't have anything to multiply by. It's sort of left out. We do 1 times 4, 2 times 5, 3 times 6, and the 7 doesn't have anybody, right? So this is actually not defined, right? Can't do it. In other words, the number of rows, pardon me, the number of columns in the first matrix has to be equal to the number of rows in the second matrix in order for multiplication to work at all. Okay, so we have 3 columns here. We would have to have 3 rows here in order for everyone to have a buddy, right? Every number has to have a buddy or else it doesn't work. Okay, here's a question for you. Why? Why the heck would we ever come up with this disgusting sequence of steps? What is the point? Did any of your linear algebra teachers bother to tell you that? Or did they just have you do a million practice problems without telling you why? Okay. So to avoid the does not exist, that's actually part of the question. That's not the question I was asking, but that's part of the answer. Okay. So you do have to have the number of columns in the first one equal to the number of rows in the second one, or else you run out of numbers to multiply and it doesn't work. Okay. But that's not quite what I was asking. What I'm asking is, why do we do a bunch of dot products in the first place? Why don't I just do something easier? Say 1 times 4, put that here. 2 times 5, put that here, and do matrix multiplication in the same sort of way that I did addition, but you just multiply instead of add. How come I don't do it that way? That'd be so much easier, right? Thoughts? Doesn't line up with the graph. So say more, Amber. What graphs? You mean like these kinds of graphs, or like XY coordinate plane graphs, or what exactly do you mean by that? You're guessing. Okay. So So you're right in the sense that if we did matrix multiplication the way that we did addition instead of with dot products, then the theorem that we're going to prove today wouldn't work. Okay, so that's a good reason. That's a very good reason, right? There's this theorem that we're going to get to hopefully in about a half an hour, where we multiply a bunch of matrices together, and they tell us something about the graphs that they represent, right? And if we did matrix multiplication in a different way, it wouldn't give us that same information about the graph. It just wouldn't work, right? So that's a good reason, but that's not actually the reason I was thinking of. There's actually a much more, rather than spectral graph theory, there's a much more sort of obvious interpretation of matrices, which is why they were developed in the first place. Not, well, that's kind of a lie. They were kind of developed for both. But, sorry, David, you said to keep the weight of all the numbers in the matrix. Yeah, that's a way of putting it. Yeah. What do you mean keep the weight of them all, though? Can you say more about that? Can you be more specific? I mean, to sort of, while you're typing, to sort of expand on what you were saying, this number 16 isn't only affected by the 1 and the 4. It's affected by the 1, the 4, and the 2, and the 5, and the 7, right? All 4 of those numbers go into building this 16, right? Oh, I'm sorry, the 4 and the 6, not the 5 and the 7, pardon me. The 1 and the 2 and the 4 and the 6 all go into making that number 16, right? But why are all of them involved, right? And you're saying to keep the weight of them all in there, which is, that's not a bad way of putting it, but what exactly does that mean? Yeah, each number will impact the others, right? So there are lots of different things in the matrices that are impacting each other. And my question is, why? What are we trying to represent with these matrices, right? I mean, there must be some reason why all the other, a bunch of other numbers would impact the result. And my question is, well, why is that? And of course, the answer is because these matrices are representing something that requires that multiplication work in that way. But what are we trying to represent here? What's the point of matrices? Transformations. Awesome. That's exactly right, Luke. Just say more about that. What's a transformation? What does that mean? A matrix represents a linear transformation when multiplied by a vector. Perfect. That's exactly right. But that's a very technical description. Can you say it in plain English? Good. It can represent something like a shear or a rotation of a vector, right? So when I talk about a vector, what I mean by that is something like this. There's a vector, right? And this is the XY plane, okay? Now I could turn that vector into another vector, okay? I could transform it, okay? So one thing that I could do is I could, I could take the whole space and I could rotate it 90 degrees, okay? So essentially, I could do that, right? And now I have a new vector. If I were to draw that, right, it would look kind of like this. And I would go, okay, so it's close to this guy, there, like that, and it goes down this way, right? So if I took this guy, right, and I rotated it 90 degrees around the origin, I would end up with this one, right? And that's called a transformation. I've transformed this vector into that one. And sorry, I shouldn't have used an arrow. This is not another vector. This is just meant to indicate that this one turns into that one, right? And what I can do is I could have this be represented numerically, right? I could have this vector in terms of numbers of the coordinates of the the head and the tail, right? And if I were to multiply those numbers of the vector by a special kind of matrix, I would get out this new vector. And I could compute where the head and tail of the new vector are by using matrix multiplication. Okay. The whole purpose of, not the whole purpose, but one of the two purposes of matrices is to understand what are called linear transformations. Okay. What is a linear transformation? That means that if you have a line, it stays a line. Okay. What kind of transformations can do that? Well, if I have a line in the plane and I rotate it any kind of way I want around any other point in the plane, it will still be a line after I'm done turning it, which you can see here, right? I could fix a point, rotate this thing, and this is still a line. Or I could rotate it around this point. Okay, yep, still a line, right? That's a linear transformation. What else could I do? Well, I could shear. So what does shear mean? There's a simpler word for that in English. It's absolutely the correct technical term, but let's try to make it easy. Shorten, yeah, I could shrink it, right? That's shear in this direction, right? If I was to shear the line this way, it would get shorter, right? Okay, or of course I could make it longer, right? If I went the other way, I could make this, this shear, but I could also, do a shear in, some other direction, like that direction, right? So the word I'm looking for here is stretch, right? I could imagine that I have, oh man, it would have been great if I, 1 second. Okay. Good thing the sewing drawer is right next to my desk. Okay, so if I've got this guy here, all right, I draw a vector on this guy. Okay, what I could do is I could stretch it like this and it'll get longer, or I could sort of shrink it. It's not working very well because it's wrinkling, but you get the idea. And a non-parallel stretch, I can make it almost straight, right? If I stretch it not in the same line as the vector, but instead I stretch it, if I stretch it perfectly perpendicularly, it wouldn't do anything. It would just sort of stay there. It would sort of shrink it a little, right? But it wouldn't change the direction. But if I pushed up this way and down this way, so it sort of went like that, that'll actually change the rotation of it a little bit, right? All of those are called linear transformations because when I do those transformations to a line, it stays a line, right? It's still a line by the time I'm done stretching it. Well, what if I did a bunch of different shears? I sheared up here and down there and up over there. Well, that would make it kind of wiggle, right? And that is not a linear transformation, and you cannot represent that with a matrix. But the whole point of linear algebra is studying matrices, the purpose of which are the entire set of transformations that you can do to a line that leave another line in its place when you're done. Yeah. It's all about how you can stretch and warp and rotate and move around a plane. And you can represent all of those transformations numerically using matrices, right? And let me just say, it doesn't have to be a plane. It could be three-dimensional, right? Now you just understood why the matrix has its name. Excellent. Good. That's great. Very nice, right? The same thing, you can do the same thing in 3 dimensions, right? You could have, this whole situation that I drew here, this could all be taking place in 3 dimensions, right? And you could also stretch and rotate around in 3 dimensions and shear in different ways. You can also translate, I should mention that, right? You could just take a vector and just scooch it over, right? Yeah, Neo is a super math guy, right? He can stretch the world as he sees fit, right? Non-linear transformations, though. So yeah, he's past linear algebra. um, well, okay, so I stretched the I translated the truth a little bit. I sheared the truth a little bit there, because yeah, you have to put an extra dimension in if you want to do translations. You can still use matrices to do them, but you have to do kind of a little sneaky trick with the matrix in order to get translations, which just means scooching. In order to get that to work, you have to do a little trick with the matrix to get that to happen, which is fine, you know. And so Lucas, you're exactly right. Using the matrices that we've been talking about here with just multiplication, it doesn't quite work that way. But OpenGL, as you said, you're exactly right, does that precise thing, right? It does this little trick with the matrices to allow translation to happen. By the time you have translation and stretching and rotating, that's all the transformations you can do on a line that leave it as a line, right? Without making it twisty or curvy, right? So that's why matrices are there and why we're interested in them, or one of the two reasons. The other reason is because of graphs, right? And we're going to talk about that in a little bit. I think that's a good place to take a break for a minute. Let me just pause there for a second. Does anyone have any questions about that? Does that help sort of recontextualize linear algebra for you a little bit? Because, man, when I took linear algebra, my professor never told me why the heck we were doing any of these stupid problems. So I hope that helps a little. Any questions for me? Yeah, definitely. Now, when you take linear algebra, if you haven't yet, then when you go in, you know, your professor will know about all this stuff. It's just not usually included in the curriculum in any meaningful way. So if you're going to take linear algebra, ask them about this. Be like, what is this matrix actually doing? What is the actual representation of the linear transformation in a space? And correlate that to the matrices involved, because there's different patterns that correspond to different transformations. So let me give you a quick example before the break, right? So if we want to talk about rotations, for example, come back on here, right? Rotation matrix. There's a special kind of matrix called a rotation matrix where the angle that you're rotating by is theta, and you put a cosine in the top left and bottom right, sine in the bottom left, and a negative sign in the top right. And if you take a vector and you multiply it by a matrix like this for some theta, it will rotate that vector theta degrees, or theta radians if you're doing radians, around the origin, right? So that's one particular kind of transformation matrix, and there are many others, right? And I'll let you go investigate that on your own time if you'd like to learn about that. Yeah, cool. Okay, so that's great. So why don't we pause there? Let's take 10, and we'll come back and jump back into some more matrix manipulation. See you soon. Okay, so I did want to say a couple more things that I realized over the break here about matrices and their related transformations. I realized I didn't ever come to my point about matrix multiplication, okay? The reason why we multiply matrices the way that we do is because matrix multiplication corresponds to multiple transformations of the same space. Okay, so let's say that I wanted to rotate the space and then stretch it. Okay, to do that, you know, I can imagine that, you know, visually happening. But if I wanted to take an actual vector numerically and see where it ends up, again, numerically, after I rotate it and stretch it, to do that, I take the rotation matrix that I used and I multiply it by the stretching or shear matrix that I used. And so composing, in other words, doing multiple transformations one after another, is equivalent to multiplying those transformations corresponding matrices. And that's why we multiply matrices in the way that we do, so that we can chain together a bunch of transformations, right, and see where the vector ends up as a result. And we do that by multiplying in this weird way where we use the dot product. Okay, so that's why matrix multiplication is the way that it is. And while we're on the topic of transformations, maybe you'd want to rotate a vector, and then maybe later you want to rotate it back, right, and undo that transformation. Okay, that's called the inverse of a transformation. Again, we're talking with sort of the terminology that we were using in chapter 7 about functions, right, where you can compose functions, you can find the inverse of functions, right? A function really is just a transformation of sorts. And so you can do the same thing with transformations. You could, do multiple transformations. You could undo your transformations, do an inverse transformation. And so a huge topic in your linear algebra class is which transformations can you find the inverse of? Which transformations are undoable, right? Not impossible, but able to be undone is what I mean by that. And there's a whole study, which usually is about half your linear algebra course, of finding out how to undo a transformation. Well, if doing multiple transformations is multiplying them, what arithmetic operation do you think corresponds to undoing a transformation? Any thoughts? If I multiply by 4, 5, 6, 7 to give me a new transformation, how do you think I would undo that transformation? Yeah, division, right? So if I wanted to undo this thing, then I would divide by that same matrix. Now in linear algebra, you don't call it division, you call it multiplying by the inverse, which really is the same thing, right? Because if I say, 5 times 1/5, which equals 1, right? What I'm doing there is I'm multiplying by the inverse of that original operation. And so there's a whole study in linear algebra about which matrices can be inverted, because some can and some cannot, right? And that depends on your transformation that you did, right? Now, it seems clear that with a rotation, well, of course, you can undo it, right? And that's a theorem in linear algebra that every rotation matrix is invertible, okay? Stretching can also be inverted, right? You could stretch it out and then, squish it back, right? So, so a shear along the axis of a vector is also invertible. And there's a whole study in linear algebra about what's invertible and what's not, right? I'll leave it you guys to think about if you can come up with a transformation that's not invertible, right? And what kind of matrix that would correspond to. That's kind of a fun thing to think about. Okay, so let's get away from sort of this interpretation of matrices and their applications to vector transformations in the coordinate plane. And let's circle back to our discussion of matrices and their application to graphs, right? And there's a lot of them here. Your book just focuses on one, and then I'll mention a couple others just offhanded, right? So maybe I should just jump in. I'll just show you what's in the book, and I think that'll be, well, now let's do an example. Okay, this is gonna be great. So this guy. All right. So let's say that we have a graph, right? Yeah, and David, you have exactly the right idea there. Multiplying by 0 is not undoable, is not able to be undone, right? Because if you multiply something by 0, like 5 times 0, there's no way to invert that to get the 5 back out, right? So David, you're absolutely on the right track there, yeah. So what I want to do is I want to show you an example of the theorem that's sort of the main thrust of section 10.3, which is all about counting the number of walks in a graph, okay? So let's make a graph. Let's find its adjacency matrix, and then we're going to compute the number of walks that are there. So let's do a 4. Let's stick with one of our 4 vertex graphs. Why don't I do a square and a loop and maybe 2 parallel edges down the diagonal? How about that? That's a nice one. Okay, I'll call this, you know, A, B, C, and D. And let's find the adjacency matrix that corresponds to it, right? So here's our adjacency matrix. I'll just put some little labels up here. So what's the first row going to look like? First row of our adjacency matrix. Actually 1110. So this only counts as one edge, even though it contributes 2 to the degree. This loop only counts as a single edge. Does that make sense, David? Yeah, cool. Okay, how about the B row? What have we got here? Okay, 1, B to B, 0, B to C, 2, B to D, 1. Perfect. Okay, the third row. Okay, so the C connections to A, B, C, and D. What have we got here in this third row? Okay, so the number of connections from C to A. What have we got? Okay, 1, 2, 0, 1. Nice. Okay, and then the last row, D. 0, 1, 1, 0. Perfect. Okay, you notice this is an undirected graph. So my matrix that I get out is symmetric, which means that you can flip it over the diagonal like this, right? Okay. Now here's what I'm going to do. I'm going to take this matrix. I'm going to exponentiate it, okay? Raise it to a power. And what's going to happen is when I raise this to a power, like let's say I want to raise it to the 4th power, what's going to be the size of the matrix that I get out as a result? What will be the dimensions of that table of numbers? Let me do cubed, just so I'm not confusing everybody. Do cubed. So if I cube this matrix, it's not going to have any effect on the dimensions. It's still going to be the same. What will be the dimensions of my answer if I multiply this by itself 3 times? How many rows and how many columns will I have in this result? Okay, so if I just take 2 square matrices and multiply them, what's the size of the answer? What's the number of rows and columns in the answer if I take 2 square matrices and multiply them together? Yeah, the same as the inputs, right? So if I take 3 of them and multiply them together, well, same thing, right? So this is going to be still a 4 by 4 matrix as my result, right? Let's find that result. And let's cheat. I was thinking about doing it by hand, but it's going to take way too long and be super boring. So I'm going to cheat. I'm going to find a website that'll do this for me. So let's see if I can find one. There we go. All right. Where do I put my matrix in? Can I just get rid of that? To the, see if that works. Give me the answer. Okay, cool. So let's make a bigger one. So I want a 4x4 matrix. Let's see, how do I? Okay, here we go. 4x4. Okay, on a 4x4 matrix raised to the third power, and let me put the entries in from our paper that we had. So it was 1, 1, 1, 0. Next row, 1, 0, 2, 1. Next one, 1, 2, 0, 1. And the last one, 0, 1, 1, 0. All right, so cubed, click go. And let's see what we have here. Okay, and there's our results, right? 9, 11, 11, 6, 11, 9, 17, 8, etc. So let me copy that down. 9, 11, 11, 6, 11, 9, 17, 8, 11, 17, 9, 8, and lastly 6, 8, 8, 4. Okay, cool. Now, why have I done this? Right? Well, it turns out that when you exponentiate a matrix, the exponent that you raise it to is the length of a particular walk. Okay? And what this is saying is how many different walks there are of this length between the row and column designator in that matrix. So let me give you an example. Okay. This number 6, what this is telling me here is that there are 6 different walks from A to D of length 3. Okay. So I want to walk from A to D, taking 3 edges. How can I do that? Well, I could go the loop on A and then CD. So I could go, let's list them out. A, C, D, that's 1. I could go A, B, D, right? I could go A, C, B, D, right? Like down, up, down, right? I could go A, B, C, D. What else can I do? That's only 4 of them. It says I'm supposed to have 6. So can anyone see the last 2? Parallel. And then these same ones on the parallel edge. So I could also do these ones on the parallel one, right? I could go A, B, C, D on this one, or I could go A, B, C, D on this one. So there's 2 of each of those, right? So 6 total. Let's try one more. Let's say I want to go, let's do D to D. It says there's 4 of them, right? So I want to go from D to D with a walk of length 3. So can someone list out one of those walks? Maybe I should label these edges instead of the vertices. Let me do this differently. 1, 2, 3, 4, 5, and 6. Okay, so which edges do I want to take? Let's do that instead of letters. To go from D to D in 3 edges. Okay, 3, 6, 4. Right? So 3, 6, 4 brings me back to D. Okay. What else? Four, 6, 3. Okay, 4, 6, 3. Great. 2 more. Okay, 4, 5, 3. Good. 4, 5, 3. Yep. And one more. 3, 5, 4. We already got that one. So what's the other option? Perfect. 3, 6, 4. Nice. 3, 6, 4. So it looks like there's a lot of ways to get from B to C. There's lots of ways of doing that in 3 steps, right? The combinatorics here is what's causing this number to be so large. I could go, around this way, take a loop. I could go around the other way. I could, go back and forth and up, and lots of different ways to get from B to C, right? Okay. So should we do one more example, or you guys get the idea? Let's do a different graph. How about that? So here's what I want to try. Let's try a directed graph instead of an undirected graph. It'll still work just fine, right? So let's do this. Let's do a pentagon. Okay. So there's my little house picture, right? Let's call these A, B, C, D, and E. Now my matrix is going to be 5 by 5 this time, right? A little bigger. Okay, so let's fill in the adjacency matrix. Does A connect to B? Oh, sorry, does A connect to A? Let me do one of these. I'll do a loop on one of these guys. Let's do a loop on A. Let's do a loop on D. I'll do that. So it's out of the way a little bit. Okay. So does A connect to A? No. A to B? Yes. A to C? Yes. A to D? No, it's going the other direction. It's going D to A, right? So this one's a 0. This one's a 0. Everybody happy so far? You think you can do the next row? How about B to A? 0. B to B? 0. B to C? 0. B to D? 1. And B to E? 0. Cool. Okay, how about C? So C only connects to E. Doesn't connect to anything else, right? So 1, 2, 3, 4 zeros and a 1. Right? How about D? Just list out the things that D connects to. How about that? E and A and one more, and itself, D. The other ones are zeros. And what does E connect to? Only A, right? Nothing else. This is the only arrow coming out of E. So the rest are zeros. Okay. So let me pop back over to this website here. Just one moment. Let's do a 5 by 5. Let me remove this. And let's do walks. Oh, sorry, let me share here. would probably be helpful. Okay, so there's a matrix 5 by 5. I want to raise it to, let's say, the 4th power this time. And here's my contents. I've got 0, 1, 1, 0, 0. That one's a typo. Okay. Next row, 0, 0, 0, 1, 0. Next one, all zeros and then a 1. Next one, 1, 0, 0, 1, 1. Last one, 1, and then all zeros. All right, here goes. All right, so there's my answer, right? Okay, cool. So what should we check? What paths of link 4 do you want to look at? From which letter to which other letter? While you're telling me, I'll label these. 1, 2. So where should we investigate? From where to where? D to D. Okay, so from D to D, how many paths does this matrix say there should be? 4. This guy right here, right? The D row and the D column, from D to D, there should be 4 paths. Okay, so what are my options here? Let's see if we can list out all 4 of the numeric sequences of which edges to take. Well, there's one that's really easy. What's the easy one? DDD, or I would say take the loop, right? So I'll say 7777. I'll do it by the numeric edge labels, right? 7777 goes from D to D, right? Okay, so what's another one? Seven, 4, 1, 3. Excellent. Right? You go on yourself, 7, 4, 1, 3. And if I have 7, 4, 1, 3, there's a slight modification I can do there to get another one. What if instead of doing the loop first, I do the loop last? What would be the sequence there? Yeah, 4, 1, 3, 7. Right? So I go 4, 1, 3, 7. Okay, there's one more. You see it? Excellent. 8, 5, 1, 3. Right? 8, 5, 1, 3. And there's all 4 paths of length 4. Right? Now it says from A to C, which number would that be in here? The paths from A to C. 2. Okay, so you think it's this number. How do you know it's not this one? Is that the paths from C to A? Which one's which? Okay, so we should be able to figure it out, right? So if it's from A to C, it'll be 2. Or if from C to A is 2, then it should be 0. So let's figure out which one's which. We should be able to just look on here and figure it out, right? So let's do A to C first. Are there any paths of length 4 from A to C? 2652. Okay, 2652. Right, very nice. So from A, we go to C, and then around this little, oh, well, yeah, this one goes up. Yep, that's right. Perfect. Okay, so I guess that's this one, right? So Amber, you were right the first time. Excellent. And so what's the other one then? One, 3, 4, 2. Very nice. Right? 1, 3, 4, 2. Beautiful. And so there shouldn't be any walks of length 4 from C to A, in theory, right? So the only place I can go from here is down 1. The only place I can go from there is up to here, so that's 2. And now I have choices. I can either go to the right, which makes 3, and then I have to leave, so that way doesn't work. To the left, that'll be 3, and from here I can't get to C in one step, right? So that appears to have 0 paths of walks of length 4. Nice. Another reason why matrix multiplication sort of takes input from or influence from a bunch of different parts of the matrix and smooshes it together is because you have to look at all the ways these different arrows are interacting in order to come out with all these different walks, right? And your book actually has a detailed proof of why this works, right? So you should definitely look through that if you have the time. But I think you can see the idea of matrix multiplication, sort of using multiple parts of the matrix and combining them together is required to look at all these different walks, because these are all like combining different routes you can go all over the graph, right? So it sort of makes sense that matrix multiplication would have to use different parts of the adjacency matrix in order to figure out that question, right? People happy with that? Does that make sense? Yeah, pretty nice that it works out so well, right? So let me talk about just quickly about a couple other things you can do with spectral graph theory, just about the things that we've learned about, okay? So we've learned about whether a graph is connected and whether a graph is bipartite. Can someone remind me of the definitions of those? What does it mean for a graph to be connected? Okay, connected means there's a walk from every vertex to every other vertex, right? So let me give you a little example. Is this graph connected? Is that a connected graph? Sorry, it's kind of gross. These are supposed to be single vertices here. Is that a connected graph? Yes, right? What if I put a triangle over here? Now is it connected? No, right? Because there's no walk between this vertex and this vertex, right? You can't get there, there's a gap, right? So to connect these, what I would have to do is draw an edge between these two components, right? If you have a disconnected graph, as I had a moment ago, right, without this guy, right, then this would be the first component, this would be the second component, right? And to connect the components, I just draw an edge between them, right? Okay, so connected, there exists a walk between every pair of vertices. Okay, what about bipartite? Remember that one from Monday? someone wants to hop on the mic and explain, that's fine too. It doesn't have to be a formal definition. Just looking for the idea here. Okay, David says you can separate the graph into two distinct regions which relate to the other region, but the points don't relate to any other in the group. So I'd say you can separate the vertices of a graph into two parts where the edges must go from one part to the other, but cannot be inside the same part, right? Which is what you said, David. I just want to give it a little bit cleaner language there, right? Okay, so it turns out that there is another kind of matrix you can make from a graph. This is called the adjacency matrix, but there's another kind of matrix called the Laplacian matrix, which is the adjacency matrix minus the degree matrix. So you might be asking, okay, well, first of all, who cares? And second of all, what's the degree matrix? So let's start with the degree matrix. Let's see what that is. And let me use my example from above here. I've got my square, the parallel edges like that, and a little loop on the top here. So let's use this guy. We already know the adjacency matrix is 1, 1, 1, 0, 1, 0, 2, 1. I'm just taking it from up here. 1, 2, 0, 1, and 0, 1, 1, 0. Minus the degree matrix. And the degree matrix, to make this one, on the diagonal, you put the degree of each vertex. And everything else is 0. Okay, so what's the degree of vertex A? Okay, 4. Nice. Okay, what's the vertex of degree B? Or what's the degree of vertex B? Also 4. Nice. C? 4. And D? 2. Excellent. And all the rest of the entries are 0. And that's called the degree matrix. Lots of different matrices you can build out of graphs. Right? So there's the adjacency matrix, there's the degree matrix, and if I subtract those from each other, what I'll get is called the Laplacian matrix, named after Pierre Laplace, a French mathematician a couple hundred years ago. Okay, so what I'm going to get is -3, 1, 1, 0. Right? Remember, I just subtract things from the same spots. Right? So 1, -4, 2, 1. 1, 2, -4, 1, and 0, 1, 1, -2. And this is called the Laplacian matrix. Okay. Now it turns out that if you find the Laplacian matrix of a graph, you can find its eigenvalues. Does anyone know what an eigenvalue is that took linear algebra? Someone explain what that means? Or maybe eigenvectors, if that's easier for you. Anyone remember? Okay, so let me help. So people remember those words, right? People remember those words from linear algebra? Yeah, I hope you learned about those for those 6 or 8 people that took it. Sound familiar at least? You remember they exist. You don't remember. Okay, so let me help. In German, the word eigen means true or essential, right? So an eigenvector is a true or essential vector of the matrix, okay? And what that means is it's a vector that remains unchanged in its direction by the matrix transformation. So for example, in my little sample from before, here, if I was to think about the matrix that stretches the plane this way, then this vector would be an eigenvector for that particular stretching transformation, because its direction wouldn't change when I stretched it, right? If I was stretching it this way, like that, right? Or even squishing it this way, either way, right? Then this would be an eigenvector for that transformation, right? They're kind of like roots. Yeah, that's right. They're things that remain unchanged by the transformation, right? Which is a little bit like a root, because that's the, a root is sort of like when you plug something into a function and you get 0 to come out, right? And here there's 0 change in the direction. So it's a little bit like a root. It's a similar sort of idea, right? An eigenvalue instead of an eigenvector, okay, an eigenvector, the direction remains unchanged by the transformation. An eigenvalue is the amount that the vector, the eigenvector, either gets stretched or squished by the transformation. Because if I stretch this way, right, then of course the vector will still be pointing the same direction, but it's going to get longer because I'm stretching it, right? And the eigenvalue is how much that gets stretched, which is just a number. If I stretch it and double it, then the eigenvalue would be 2, right? If I take this one and squish it a bunch, right, like squish it by a factor of 4, then the eigenvalue would be 1/4, right? And you can do all kinds of algebra, that's why it's called linear algebra, to actually, run some equations and figure out those numbers, right? It turns out that if you take the eigenvalues of the Laplacian matrix, you get out a number of eigenvalues that's equal to the dimension of the matrix, assuming that it's not a degenerate case, which I won't get into that. But for the sake of argument, we'll say the number of eigenvalues that you can find from a matrix is just equal to that matrix's size. So there'll be 4 of them in this case. It turns out that if the first largest eigenvalue is equal to 1, sorry, you have a question, David. For an eigenvector, the magnitude can change, but the direction can't. That's exactly right. And the amount that the magnitude changes is called an eigenvalue. That's the amount of that change in magnitude. Does that make sense? Got it. Cool. It turns out that if you find the Laplacian matrix and find the eigenvalues, which is an algebraic manipulation, you do run a little equation to find them, then the first or largest eigenvalue, if it's equal to 1, then your graph is connected. And if it's less than 1, then your graph has more than one component. So you can actually tell if your graph is connected by finding the eigenvalues of the Laplacian matrix. If you look at the last eigenvalue, the smallest one of your Laplacian matrix, that'll tell you whether or not your graph is bipartite, right? So these really, really sort of intuitive visual properties of these graphs can actually be computed algebraically according to the Laplacian matrix and finding its eigenvalues, which is pretty wild. Would be more wild if you remembered what an eigenvalue was from linear algebra, but context always helps, but doing the best we can, right? So, it's not just the number of walks you can look at, but there's lots and lots of different kinds of properties of graphs that you can investigate using matrices and linear algebra, which is pretty cool. Questions? What do you guys think? The largest eigenvalue tells you whether or not the graph is disconnected. If it's less than 1, then that means the largest eigenvalue, or I should say the ratio between the two largest eigenvalues gives you in some sense a measure of the connectedness of the graph, sort of like the average degree a little bit. And so it's an interpretation of it. And so, yeah, makes sense. Cool. Yeah, okay. So there's a little bit more about spectral graph theory. Let me say the last thing, which maybe ties this together a little bit. If you find all of the eigenvalues of a matrix, that's called the spectrum of the matrix. Sort of like in physics, if you have a light wave, so you're measuring some light, and that light has a spectrum of the different wavelengths that go to create that beam of light. You're doing the same thing here, right? In physics, when you have the spectrum of a light wave, you're figuring out all the different colors of light that are combining to make that particular, light beam that you're looking at. Here, you're looking at all the different vectors that combine to give you this particular matrix transformation. So it's sort of like decomposing something into its component parts is what a spectrum is, right? And that's exactly what we're doing here. We're taking a transformation and decomposing it into its eigenvectors, which are the directions that it's being stretched in, basically, right? So if you want to stretch it this way and this way and this way, all to different amounts, the amounts that you stretch it would be the eigenvalues, right? And you put all that together into a single matrix, right? That would be the spectrum of that matrix. And that's why this is called spectral graph theory, because you're looking at eigenvalues and eigenvectors of a matrix representation of a graph. Right? Sound good? Other questions? Okay, cool. So I want to touch on section 10.4 really quick, and then jump into the lab in the last few minutes here. Section 10.4, which I believe is now 10.3 in the new edition, edition 5, is all about graph isomorphisms. And we talked about this a bit on Monday. And so can someone remind me of what a graph isomorphism is? Okay, so close. So you remember that one. That's actually not a graph isomorphism. It's a topological isomorphism. So that's a little bit different one. Yeah, and Luan, you got the idea. It's the same formed graph, right? So for example, a pentagon and a star are isomorphic, right? Because you can sort of unwrap the star and pull and shape it into a pentagon, right? Or, and here's the little symbol for isomorphic. It's an equality with a tilde on top, right? So you could also have, this situation. Those two graphs are isomorphic because all I have to do is take that one and twist it, right? Rotate it 90 degrees and I'll get that one popping out. And we talked about that sort of in general, but your book goes into a bit more detail talking about how graphs are isomorphic, okay? Or how you can judge whether or not they're isomorphic, okay? And the way that you do that is actually pretty straightforward. There are lots and lots of properties of graphs that we've talked about now. We've talked about if they're connected, if they're bipartite. We've talked about walks of a particular length. We've talked about the degree list of the matrix, right? If two graphs are isomorphic, then all the properties of the graphs have to be the same. And that's a really nice way of trying to figure out whether or not two graphs are isomorphic, is you just run down a list of properties of the graphs and make sure that they're all the same. And if you find one that's different, well, then you know that the graphs are not isomorphic, right? So let's do some examples. Well, let me give you the list first. Here's the list, right? Here's a list of graph properties that you can check to see whether graphs are isomorphic. Well, of course, they have to have the same number of vertices and the same number of edges. That would be a dead giveaway, right? They have a vertex of a specific degree, or they have a certain number of vertices of a specific degree. In other words, just the degree list, those have to be the same. Whether they have a circuit or a simple circuit or a walk or a trail or a path of a certain length, You could check all of those things. And if one has a simple circuit of length 5, then the other one better have one as well, right? If they're connected, right? Or how many components they have, that's got to be the same. Whether or not they have an Eulerian or Hamiltonian circuit, it's got to be the same. If they have multiple Eulerian circuits or multiple Hamiltonian circuits, the number of those that they have has got to be the same, right? So there's, you know, I even expanded upon this. There's maybe a dozen or 15 different properties you can check on a graph to see if they're the same or not, right? So let's do some examples. Show that these are not isomorphic by finding an isomorphic invariant. That's one of the things on the list that's got to be the same. That's an isomorphic invariant. Invariant meaning doesn't change, doesn't vary. And these are the isomorphic ones. So this is just, you know, find something on the list that doesn't match, right? So for this one, graph G and graph G prime, can you tell me something that's different about those graphs to prove that they're not isomorphic? And actually, let me do this. Wrong way. I'll give you the list and the pictures just to start with here. Too many edges. Okay, so here this has 1, 2, 3, 4, 5, 6, 7, 8 edges. This one has 1, 2, 3, 4, 5, 6, 7, 8. Well, no, I think they both have 8, unless I counted wrong. 1, 2, 3. Wait. Yeah, they both have 8. It's hard to count. I had to do it 3 times, so don't worry about it, David. Yeah, that was hard, but they do have the same number of edges. Okay, so other ideas? The left one has 9. Did I count it wrong 3 times in a row? 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, I totally counted it wrong 4 times in a row. Yep. The left one does have 9, and the right one, wait. Nope, it doesn't. It has 8. I'm going to label them because that's really annoying. Yep, it has 9. Very nice. Wow, I don't know why that was so hard to count. Too many overlapping triangles. Okay, and the right one has 8. So they can't be the same because they have a different number of edges. Perfect. Okay, wow, that was terrible. All right, let's try the next one. Does this one have the same number of edges? It has the same number of vertices. It's got 5 on each. Have the same number of edges? Yeah, it does. They both have 7. Okay, so the edge count is not going to work for us in this case. So what else can I use? Hamiltonian circuit. Ah, very nice. Okay, so this one does, but this one doesn't, right? You're not going to be able to, oh, no, this one does actually. No, this one does, because you can go make a little sort of envelope shape. Yep. Yep, so they both do, actually. Okay, other ideas? Okay, the vertex degrees. So in H prime, there's not a vertex of degree 4. There is right here. So here's a vertex of degree 4, 1, 2, 3, 4 on the left. But on the right, we've got a 3, 2, 3, 3. Yep, very nice, Amber. Yeah, so the degree vertex degrees rather is your saving grace on that one. Okay, let's do a couple more examples. Set this down here. All right. So let's do number 12. That's a cute one. Are these two graphs in 12 isomorphic? Yes, okay. And can you describe to me what you do to go from one to the other? How you would sort of move things? Yeah, you just keep rotating the inner square, right? Until things, well, I think it might be easier if you rotate it a little bit and then take the square and flip it upside down, and that'll make the lines cross. Does that make sense? Like a rotate and a flip? Yeah, I think if you keep rotating, then the edges are going to cross each other. But this edge is going to cross this one if you keep rotating, rather than this edge crossing this one. Does that make sense? But yeah, cool. Okay, you have the right idea. Okay, what about number 11? Are those isomorphic? No. Okay, why not? 6 vertices, all degree 2. Ah, but G is disconnected. This is actually 2 different components, right? This is 2 separate triangles that are just sitting on top of each other. They're actually not connected, right? Everyone see that? So G is not connected, but G prime is, right? Very cool. Okay. So how about number 10? In fact, why don't we just stick over on this side? So this one here, I'd call a ring graph, right? G actually is connected. So watch, right? If I go A, C, E, G, B, D, F, A, I can get back to where I started, right? So it actually is connected. It just looks kind of sneaky, right? Yep, sneaky. So do you think they are isomorphic then? We have the same number of vertices, right? 7 of them, and every vertex is degree 2 on both graphs. So yeah, it turns out they are isomorphic, right? Yeah, very nice. Let's do one more. That one's easy. These are isomorphic, right? You take WX and unfold it down here, right? WX and sort of flip it down on the bottom, and you can see it makes that little ladder kind of thing that we have over there if you stretch it a little. Let's do an interesting one. How about 13? What do you guys think about that? I mean, of course, this one is the same as this one, so it must be isomorphic to this one, right? So if you have, and this, this right here is what's called the cube graph, right? Because if I was to draw a cube, looking at it from the front, real quick here, lost my cardboard there. So if I draw a cube, looking at it from the front, it looks like this, right? So that's the cube graph. And the question is the cube graph isomorphic to a cube graph with a twist in it, right? There's a single twist, yeah? So what do you think? You think so? David says no. Okay, so let me ask you then, David, since you're saying no, what property of the graph that you did you find that was not satisfied in this one? Or what's the difference that you found? Let me put it that way. Like which property is different in the 2 graphs? Okay, you tried imagining untangling the lines. That's great as an intuition, but the actual proof that they're non-isomorphic, there has to be a property that differs between them. So you're on the right track with untangling the lines, but think about when you're untangling the lines, what that's going to mean in terms of the properties to try to find the property that's different between the 2. Does that make sense? Okay. So and while people are thinking, David, let me explain. I think what you were thinking about, if you untangle this thing, maybe you would flip B and C this way, right? To untangle them. But that's going to make a tangle between A, B, and DC. There'll be a big X in the middle here. Well, I could untangle that by flipping A and D, but then that's going to make these two edges cross, right? Well, I could uncross those by flipping EH, but then these two lines would be crossed. I could untangle that by flipping F and G, but then I'm back to where I started. So every time I try to untangle, the tangle just moves down to the next pair of vertices, right? So I get your point. That's an excellent way of thinking about it, but it's not proof, I wouldn't say, right? Any other ideas? Okay, well, we're out of time. So let me tell you the answer. Okay, this one has a circuit of length 5, D, H, G, B, C, D. This little sort of step shape here, a circuit of length 5, and G prime does not, right? So if you include that twist in a circuit, that's going to give you a different length of the circuit than if you didn't have a twist, like in this one, or in this case, a double twist. So I could go V, W, X, U, V, and that's only a circuit of length 4. In fact, there are no odd length circuits in this guy at all, right? Does that make sense? People happy with that? Nice. Cool. Okay, so let me, if you've got to go, then we're at the end. So if you've got to go, that's fine. But let me take about 5 or 10 more minutes to talk about the lab if you all want to hang out, right? So let me stop the video here. Okay, and I'm going to share screen. So sorry, I'm running a little bit over today, but as always, there's too much to do and not enough time. Oh boy, and it logged me out, of course. That. Get that up and running. Okay. Let me get our lab for this week here. All right, lab 7. Get the project open, that'll take a while. Okay, let's download this. Oop, Can you hear you? Okay. Okay, good. Got that guy. This one's still loading. Okay, so let me talk to you for a minute while this is loading. This week, we're going to still be in 3D as before, but what we're going to do this week is you're going to be drawing a graph in 3 dimensions, okay? Now to do this, we're going to have to represent a graph in C++, right? So we're going to have to find a way of making a data structure to store the information in a graph, and then from that data structure, use that data to draw a picture in 3 dimensions. That's the plan, right? So what I'd like to do is show you the data structure, show you how it's drawn, and then run the program and show you what kind of a picture you can make. There we go. Cool. So here's one data structure, my point, just has X, Y, Z, right? But I also have 3 things. I've got V, which is my vertex count. I have 125 vertices in this particular graph. I have an array of vertices. Each one is a point because each vertex is going to be in 3 dimensions. So it'll have 3 coordinates, X, Y, and Z. And I have an array of V of them. V is my size of my vertex set. And then I have an array, a 2-dimensional array, which is Boolean, and that's my edge array, 2-dimensional V by V. This is just an adjacency matrix. That's all it is, right? It's got 0s and 1s because each vertex could connect to something else or not. This is going to be an undirected graph, right? So I made it Boolean because every vertex either connects to another vertex via an edge or it doesn't, right? So this is going to be my data structure. I have a two-dimensional array, V by V sized array to hold my edges, and my coordinates of those vertices, which is just stored in a single dimensional array called vert. People with me so far? I'm just making up an adjacency matrix, right? Keyboard timer. Okay, so this is all the old stuff. So here's the new stuff. Init G and draw object here. So let me start with draw object here. That's probably the easiest one. I'm going to be drawing lines this time. Draw lines. So what I'm going to do is go through in both dimensions from 0 to V through my adjacency matrix, my edge matrix, okay? And if there's an edge from I to J, right, where I is my starting vertex and J is my stopping vertex, right, the two endpoints of my edge, then I draw a line from my vertex array at point I in X, Y, and Z to my vertex array at point J in X, Y, and Z, right? So if I have a true, a 1, in my adjacency matrix, then I draw a line between I and J, which are representing my two vertices. Does that make sense? Any questions so far? Roger. Okay. So let me show you what I did. So for init G, this is what you're going to change. Okay. So you're going to set up your vertex positions and then set up your adjacency matrix, right? So here's what I've done to set up my vertex positions. I've arranged them from -1 to 1 by adding a half in each dimension, okay? So I go -1, -1/2, 0, half, 1. And I do that in all three dimensions, I, J, and K. So I have a 5 by 5 by 5 cube of points for a grand total, 5 by 5 by 5, of 125 vertices, right? So if you can imagine a cube of equispaced points, 5 in each dimension, that's what I'm making for my vertices. Now you can make whatever shape you want. This is just a goofy random thing I made up, right? But you should make your own sort of shape and decide where in space you want to put your vertices. Okay, that's step 1. Step 2 is decide what you want to connect, make edges between. So what I've done is I've said, okay, I'm going to put a 1 into my edge matrix for everything where I is larger than J, right? So J equals I plus 1. You can sort of think of my adjacency matrix as just a matrix, right? It's just a table. And what I've done is everything on the upper right diagonal, everything above the diagonal is equal to 1, and everything below is equal to 0. The reason why is because the matrix is symmetric, as we saw earlier. And so I only need to put 1s in half of it, right? Only on the upper diagonal part will be plenty. So if I run this, I'm going to have a cube, 5 by 5 by 5 point cube, where every vertex connects to every other vertex. In other words, it's a full adjacency matrix, right? It's full of 1s. And there you go. So you can see the 5 vertices down one side, 5 vertices across, right? If I rotate this guy, right, you can see there's 5 in every direction, right? And this is very full. There's a lot of connections there, right? So maybe I want to turn down the number of connections, right? Well, in that case, maybe I would say I only put an edge into IJ, maybe, if I plus J mod 10 equals 3. I don't know, I just totally made that up out of nowhere. It's just going to look kind of goofy, but now it's going to have 1/10 the number of edges inside, right? And you should, think, I'm just running out of time, so I can't do something very clever. But I just wanted to sort of reduce the edge count in there. So you should think of something more clever, right? So there you go. So those are all the edges. Yeah, that looks terrible. Let me try one more time. Let's say I want to do mod, let's do mod 5 equals 0. That'll do something a little nicer, I think. Since I have 5 by 5 by 5, probably if I mod by 5, it'll do something clever, right? There we go. That's kind of nice. Oh, it's just got a flat thing there. Okay, so that did something interesting, right? And I'll let you mess around with that, right? So you decide where the vertices go, and then you decide who connects to who, and make a picture. Sound good? Looks good. Okay, sounds great. And Luan, yeah, I'll get that to you, Luan, as in just a minute after class. Yeah. Okay. Well, great. Well, have a great day, everybody. Sorry I went a little over, but hopefully that's helpful for you. And I will see you on Monday. Have a good one, guys.